All right, hello everyone. Today we're just building off of what we did yesterday. We are taking on angle and arc relationships, just part 2. So I'm making it a little more complicated. So in the first problem, we're calling it circle A, and we want to find each of the following arcs and angle measures. Remember that if we call something circle A is the center of the circle. So right now I'm just looking at my little circle puzzle and I'm looking for angles and arc measures that I'm able to build off of. So the first thing that I'm able to see is right here, that's a central angle that is 76 degrees. So that means that from here to here, its intercepted arc will also be 76 degrees. So I can fill that in right away. I can also link up the linear pair. So right here, this has to be 104 degrees. Linear pairs are always supplementary. They have to add to 180. Okay, I can also see here vertical angle with the 76 or linear pair with the 104. That angle has to be 76. And then likewise over here, 104. So either linear pair connection or vertical angle connection. So I filled in all of my central angles. So now here, building off that 104, that central angle has this intercepted arc. So right here is 104. Okay, I can see that right here, this central angle, 76, has this intercepted arc. So since I already have used up 24 degrees of this full 76, 76 minus 24 makes up this smaller portion right here at 52 degrees. Okay, looking over to here, that last central angle has this intercepted arc from here to here, so it has to be 104 as well. So far, all I've been able to build off of is the fact that the center of my circle is A. So I have some central angles, and I have their intercepted arcs. So now I'm just looking for other places to build off of. So if I look, say, right here, here I have an inscribed angle. From here to here is the intercepted arc. So I'm taking half of 24 to get to 12 degrees right here. I can also look at where G is right here. So this inscribed angle, vertex on the circle, will be half of its intercepted arc. So 24 plus 52 is 76. So half of 76 gets me a 38 right here. Okay, right here where the F is, this is an inscribed angle too. Here is its intercepted arc. Half of 76, also 38. That makes perfect sense because look back here where A is. A is the center of the circle. So right here is a radius, and right here is a radius. And I know that all of my radii are going to have to always be congruent. Any one radius will always match any other radius in the diagram. So I have this beautiful isosceles triangle. I have my base angles that are congruent, right? They're both measures of 38 degrees. Okay, so now let's see what else I have to fill in. So right here I could get to this angle where E is. Vertex is outside of the circle, so I can see that it's going to be 1/2 the difference between the intercepted arcs. So if I trace it up to here, the larger of the two is 76. And then here down, the smaller of the two is 24. So I'm taking half of 52, which will get me 26 degrees. So 26 degrees right there. Okay, lastly, I see that I need these angles in this spot. So there's a couple ways I could get there. First way is just looking at the triangle. So if I look at this triangle right here, I can see that I have 104 and 12. So I have 116 degrees that are already used up. So if I do 180 and I subtract that 116, I get 64 degrees here. Okay, I could also picture my vertex that's inside of the circle. I could trace up, look at that intercepted arc, that is 76. This intercepted arc is 52. So if I add 76 to 52, I get 128. If I split 128 two ways, I get to 64 another way. We got lots of options, you guys, so it doesn't matter to me how you get there as long as we match in the end. So now lastly, I just need to connect the linear pair with the 64, which gets me 116 here and then 116 here. All right, I think I filled up everything that's possible to fill up. So now I'm just going to fill in the blanks. So GBC. So GBC, right here, endpoints GC. I'm looking at this arc right here, and that's really a semicircle. So that has to be 180 degrees. Okay, FBD. So FBD, that angle is 12 degrees. Angle E, 26 degrees. CD, it's an arc, and it's the smaller of the two, because that's a minor arc notation. So I'm looking at 52 degrees. Okay, GBF, so that tells me it's a major arc or a semicircle. So I need to look at the endpoints, G and F, here, here, and I'm going the long way. So I could either add up the 76, 104, 52, and 24, or I could do 360, subtract that 104. Either way, I should get to 256 degrees. Okay, angle BHC. So BHC, so right there is 116 degrees. And then angle FGC. So here's F, here's G, here's C. So right there, vertex G, right here we're at 38 degrees. I love the circle puzzles, super fun. All right, next up here, we're looking at a probability question. Let me slide that up. So find the probability. So probability, let me just underline that part. Of throwing a dart and having it land in the shaded region, round to the nearest 100. And I'm saying that the triangle is equilateral. So here I just need to think, well, how do I get to the probability? Well, my probability is always going to be my shaded region, right? The area of my shaded region. And I divide that by the total area. So when I write out my master plan here, to get to my shaded region, so my shaded region here, 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 I'm looking at, well, what is the circle with that hollow triangle removed? Okay, and then I'm going to divide that by my total area. So we're assuming that we at least make it on the dartboard. So this entire shape is just a circle. Okay, so if I lay out my formulas, my circle is pi r squared. My triangle, well, it's equilateral. So I actually have some options. I could solve using my triangle formula, 1/2 base times height. But in this case, since it's an equilateral triangle, a regular polygon, I think it's going to be a little easier to do 1/2 the apothem times the perimeter. So there's my circle minus triangle. And then I need to divide that by the circle, just like that. Okay, so now that we're here, I'm going to draw out that triangle. I'll do it right up here. So here's my equilateral triangle. And I have this part drawn in right there. And that's 12. So 12 right there, that's actually a radius of the circle. And it's still a radius for the triangle as well. We're just connecting the center to a vertex. So right there is 12. So if I draw in the apothem like so, I know that for any equilateral triangle, this angle starts at 60. They're all 60. But here, this one's getting bisected. So right here would be my 30-degree angle, and this would be my 60-degree angle. So if I build off my knowledge of special right triangles, that short leg is x, the longer leg is x root 3, and the hypotenuse is the 2x. So I really know that if 2x is 12, then x is going to be 6, so that's my apothem. And then this measure that's half of a side, will be 6 root 3. So then that tells me that a full side must be 12 root 3, so my perimeter, I have 3 sides. They're all 12 root 3. My perimeter is 36 root 3. So I'm just keeping all of that in mind. One thing I just wanted to point out too, just a common mistake that I see, if I look at an equilateral triangle, Just draw one out to the side. The height of it is really made up of an apothem and a radius. So from here to here, center to a side, that's the apothem. And then center to a corner right there, that's a vertex right there. So center to a vertex, that's our radius right there. So together, it's really the apothem plus a radius that make up the full height. Okay, so common mistake that I see is that students either tend to double the apothem or double the radius to make it the height. The height is actually the apothem plus the radius. All right, so now I'm ready to plug into my formulas. So my circle is pi r squared. So here I'm saying pi times my radius, which is 12, and then squared. So again, that part right there was my radius of the circle, radius of the equilateral triangle as well. So then I'm taking away 1/2 the apothem. Apothem here is 6 times the perimeter, which we've already established is 36√3. So that formula, just again to remind you where it comes from, let me see, I have a little room up here. So if I'm looking at my equilateral triangle like this, and I connect all of these radii just like so. So if I draw in one of my apothems, right, it's really the height of one of those triangles. So I'm picturing this as a strip of 3 triangles like so, where right here is the apothem, right, it's the height of one of these 3 triangles. And then I know that this is a base for each of them, and collectively all of their bases make up the perimeter. So that's where that area equals 1/2 apothem times perimeter formula really comes from, because we're taking the height of one of those individual triangles, because they all have the same height, and then we know that all of their collective bases is really the perimeter. So we're just taking the area of all of those triangles in just one swoop. All right, back to here. So here now I'm dividing by the full circle. So pi times 12 squared. So when I clean this up, I now have 144 pi, take away 1/2 of 6, that's 3 times 36, and I'm at 108 times the square root of 3, all divided by 144 pi. All right, so I could plug this into the calculator. What I have to be really conscious of, though, is my order of operations, so I need parentheses. Okay, one other thing that I could do is I could reduce it. I know in Algebra 1 we don't do a lot of rational expressions or equations, but this is a good example where I can show you how you can simplify. So I can simplify further if all of these numbers are divisible by the same quantity. And each of these values is divisible by 36. So if I divide 144 by 36, that would be 4. 108 divided by 36, that would be 3. And again, 104 divided by 36 would get me back to 4. So I could also reduce it and make it 4 pi minus 3√3 divided by 4 pi. And I'll show you when I type it in that it's going to get me the same approximation. So I'm going to plug in both of those, and I just want to verify that I'm going to get the same answer overall. I'm looking at the probability that my dart lands in that shaded region. So I know that my probability has to be something between 0 and 1. So 0 would mean it's never going to happen. 1 is it's guaranteed to absolutely always happen. We're usually somewhere in between. So before I even calculate anything, I just want to eyeball it and make a prediction. So what would I say is the proportion of the circle that's shaded? So here I can see, if I estimate it, I'd say that it looks like it's a little bit more than like 50%, a little less than 70%, so maybe somewhere in that ballpark. So let's type in and let's see if we get something that's more than 50%, less than 70%. Okay, so let me show you with my calculator. All right, so here if I type in this one, here's my parenthesis, and I'm saying 144 times pi. If you don't have that button, you could type in 3.14 as your decimal approximation. And then we want to take away 108 times the square root of 3. Okay, and then I want to close my top parenthesis. So I'm keeping this as a group, open and closing my parentheses. Okay, and then I divide it by the package on the bottom of 144 times pi. So I hit enter, and I get about, if I go 2 decimal spots nearest hundredth, that's about 0.59. Okay, that's in my ballpark of estimation, so that makes sense. Let me plug in this reduced version just to make sure that we match. We get the same thing. So this would be about 0.59. So let's check over here, make sure it's the same. So here I have open parentheses, 4 times pi minus 3 times the square root of 3. Okay, and then from here, let me just close that parenthesis. I didn't need it. And now I look at, okay, so 4 pi minus 3 times the square root of 3. And then I'm dividing that by the package of 4 pi. Look at how my answers are exactly the same. So here I just reduced it down. And by reducing it down, I'm looking for a number that goes into all 3 of these terms here. They were all divisible by 36. So I just reduced it down, simplified it, and wrote it as 4 pi minus 3 times the square root of 3 divided by 4 pi. And again, the parentheses are crucial because it preserves your order of operations. All right, let's do a little flip or just take out that second sheet of paper for the lecture right here. So I got a big one. It's a big one. All right, so here for this one, my idea was for you to pause on this one. So I want to hit pause. Go ahead and pause. And I want you to make as many connections as you possibly can. So what I would probably do, I'd build off the angles that are marked. I'd start with my central angles, go on to their intercepted arcs. Then look for the inscribed angles, look at their intercepted arcs. Any triangles, they have to add up to 180. We know that when our vertex is inside, the angle will be the average of the 2 intercepted arcs, or 1/2 the sum. And when the vertex is outside, it's 1/2 the difference. So I would love it if you would pause for a moment, pause me, and I want you to tackle this problem. Okay, and then unpause. And let's get started. Here I'm going to go over it. So here we're calling it circle O. O is the center of our circle. We know that ED is tangent at point D. So we know that that means it's making contact in one location. HD and BF are diameters. So those diameters are going to create semicircles for us. We want to keep that in mind. All right, so let me try to make it so that you can see as much of this as possible. Okay. So first off, I'm going to build off of that central angle of 26 degrees. So if this is 26, let me trace it up. Right, I got 26 right here as well. Okay, I also know that this is a diameter. So let me flesh that out. There's my diameter. So I know that all of these arcs together have to add to 180. So if I take 180, I subtract 46, 26, and 40, I get 68 degrees right here. Okay, and then if I work around my circle, here I have another diameter. Boom, just like that. So I know that together, all of these 3 arcs, they have to add up to 180 as well. So if I take 180, I subtract 40, I subtract 68, I get 72 degrees right here. Okay, if I go back to here, that diameter, this is also a semicircle. So if I subtract 10 and 72 from 180, I'm left with 98 degrees right here. Okay, so I have filled out every arc that is around my circle. So now I'm going to go ahead and fill in any central angles. A central angle, the vertex is always the center of the circle, and it's going to have the same measure as its intercepted arc. So right here first. So from here to here would be the intercepted arc. So I'm looking at 40 plus 68. So I get 108 right here. Okay, and then I can connect to here the linear pair, right? Got to be supplementary. And then over here, it's vertical angle 108. Also linear pair with that 72. Okay, I know that right here, this is a central angle. So if this is 46 right here, then I got to have 46 right here also. Okay, so right now I've done a good job. I have marked all of my arcs and I've marked all of my central angles. So next, I would go through and I would label all of the inscribed angles. So looking for all the places where I have a vertex on the circle. So let's say that I start with this one right here, where C is. So if I trace that down, that angle should be half of its intercepted arc. So half of 72 gets me 36 right here. Okay, next up here, this angle, vertex is on the circle, so if I trace it up to here, I need to add the 46, the 26, and the 40. So that adds to, let's see, 112. So I have 112. So if I take 112 and I cut it in half, right here, I get 56 degrees right there. Okay, the angle right here, here I have a radius, here I have a tangent, and I know that where they meet, they make a right angle, right? We learned that earlier in our circle unit. Okay, moving along, going to any inscribed angles. So right here, vertex is on the circle, so this angle will be half of its intercepted arc, so 20 degrees right here. Okay, and let's see, I think that's the only other one I can get to, because I can't get to this one just yet, because I can't trace that arc over to where it intersects. So I'm a little stuck right now. So now what I would probably do is I look for any vertex that's inside, or I look for any triangle where I know that they have to add up to 180. So for example, right here, these two angles, they add up to 92. So this angle has to be that supplement, so it's got to be 88 right here. And then it's vertical angle 88, linear pair 92, and 92. Okay, what I could have also done right here where I marked that 88 is I could have seen that my vertex is inside the circle. So if I trace it over, I know it's going to be the average of 68 and here to here 108. So if I add those two and I slice it in half, I get to 88 a different way. So again, whenever my vertex is inside the circle, the angle will be the average of the two intercepted arcs. Another way to say that is 1/2 the sum. Okay, as I move myself over to here, let's say that I look at where J is and I want that angle right here. So I just need to figure out what are the two intercepted arcs. So if I trace that down, I have 98 here. And then here my other one will be 26, 40, and 68 all added together. So if I add up those three measures and I add up the 98 and I slice it in half, let me see, what does that sum to? It summed to 132. So if I take, or 232. So if I take 232 and I slice that in half, I get 116 right here, and then vertical angle 116 here. Okay, linear pair, 64. Same over here, 64. Okay, so now I think the last angle that I needed to fill in up here, right here, again, I got a triangle. So if I take 180, I subtract 116, subtract 46, I'm left with 18 degrees right here. So I think I filled in everything that I possibly could up in here. I just have to get to the two ones down below. So down below, so this one right here, I needed to do 1/2 the difference between the two intercepted arcs. So 108 minus 72, and cut that in half. So half of 36 will get me 18 degrees. So 18 degrees. And then this guy right here, 1/2 the difference between the intercepted arcs. So half of 26 minus 10. So half of 16, and we get 8 degrees. All right, so now if I fill in all of my gaps to the right, the measure of arc AB, minor arc AB, is 26 degrees. Angle BOD, so BOD right there is 108. AB is the small angle that's right down below, right in the bottom down here. That was the 8-degree angle. HGD, well, 3-letter notation tells me that's either a semicircle or a major arc. So I'm looking for the H and the D here to here and passing over G. So I'm looking at this semicircle, exactly 180. Okay, AJO, so let's see, AJO, so right there I got 116. FCD, so FCD right there is 36. Angle CKH, so CKH right there is 92. BG, let's see, here's B to G, so I have 170. GAO, so GAO right there is 18. Okay, BED, it's the other one that's down below here. So that is the larger of the two. So that was the 18-degree angle. Okay, HOF, so HOF right here, 108. And then KDE, where's my K? There's K. KDE, right, that was the 90 degrees. All right, that's all I got for today. I hope you guys are doing well. I'm looking forward to seeing you guys soon. All right, have a good rest of your day.